Okay, today I'm going to be talking about some techniques that we use on our team in managing defects in high-performance computing software development. Thank you for having me over the next, hopefully, not quite full hour. Generally, when I give presentations or talks like this, I kind of like to establish, let's see here, establish some ground rules. You know, this is an unusual format. I can't see you, you can't see me. So if what I'm saying doesn't seem really interested, but you feel guilty about checking off, you know, feel free to veg out. If you really dislike what I'm saying, profane gestures are fine. I won't see them, so hopefully you won't distract anybody with that. One thing I like to say when I'm doing anything that's related to software development, I'm not proselytizing here. I'm not saying these are things you have to do to write good software. I'm simply going to talk about some techniques that have worked quite well for us and myself and the teams I've been on over about 20 years. You can violently disagree or have other opinions, that's fine. Again, if you disagree, see back to bullet 1. I'm going to try to keep this fairly short and sweet. In the end, I always like to try to design talks, especially ones like this, where there's only a few limited concepts that are useful to take away. And in this case, there's really only one concept I'd like to kind of emphasize that we'll get to. Again, go back to item 1 if you're not interested. There's not going to be any kind of distracting manager clip art. I'm going to try to keep this relatively technical. If you really require a lot of shiny or sparkly things to keep you awake, again, feel free to veg out. So what I'm going to talk about here is basically what I call the kind of challenge of research and software development. Those things are often thought to be in opposition. Hopefully I can convince you they're not. Something that we practice that we call the complete development lifecycle. That's a term I made up. You probably won't find it in books. If you find it in books, it probably means something else than what I mean, so I apologize for that wording. I'm going to talk then about some actual techniques that we use, primarily unit testing and design by contract, and then we'll summarize at the end. Okay, so doing kind of scientific and methodology research and high-performance code development. Often, you know, SQE is kind of how do we manage software quality engineering and discovery, and this is often thought to be a real challenge, and it is a real challenge. It's often thought to be in opposition, and where you've actually will see some people say, well, you know, you can't ever manage software quality while we're trying to discover new things, or just, you know, hack this stuff together and don't get distracted by that quality engineering stuff. And there's some truth to that to a point, certainly. But let's posit something that consider a new algorithm that you want to implement in a multidimensional parallel code. You know, we're kind of beyond the range now where we're really worried about simple, you know, 1D stuff. Of course, we all do little prototyping, but, you know, in terms of doing big computational physics where we're trying to do big discovery science, which is really where HPC is engaged in, we're really trying to think about, you know, we're actually doing stuff in big models, big complicated pieces of code. All right, so I want to implement some new algorithm in there. I say I do due diligence, and I work through the mathematics and the algorithms carefully, and my theory predicts that I should get second order convergence. I do my computational results, and they come out first order instead of second order. And now I have to ask, is this a code bug or is it an error in my analysis? This is always the kind of thing that we end up fighting with. And my example here means that to some extent, the quality engineering and the methods research are not only compatible, they're really essential. Otherwise, you end up going through these cycles forever where you're trying to figure out, did I implement something wrong? Is my theory and analysis incorrect? And you spend lots of time trying to reconcile those two things. And this is really true in parallel scientific software, which is really much more difficult to design, test, and analyze than serial software. So what I'm really going to be talking about here, interested in the case where we can actually do something to perform software verification, and that's the method for removing potential defects at code construction time. Okay, so, you know, we start by defining some general terms, and we're going to keep this fairly simple. But in a nutshell, software quality engineering is really the practice of managing the cost and quality of the software process. And so this kind of gives me to my STAR guiding principles. And quite honestly, if you turned off here, you would get my one concept here, and that is the cost of defect resolution increases the time from defect introduction. There's actually a lot of literature on this, and it really kind of comes from common sense. And the reality is that when you introduce a defect, and you will, and we do, the sooner you recognize and realize that those defects have been introduced, the sooner and can attack them and deal with them, the less cost that you impose downstream. You can often find this this is often fairly obvious in kind of construction projects, right? If I'm building a building and I buy second grade steel to build the framework, and I don't test it, and then I put the building up around it, and then the building falls over or fails, that's really expensive to fix. Whereas if I start by testing my girders before I put them together, while that still imposes some cost, it's not nearly going to be the level of cost that I have to deal with if I actually build the whole building, and then obviously then have to go in and deal with the underlying foundation after the fact. So this is largely common sense, and most of SQE is simply a series of practices that are derived from common sense, one could argue, but it's something that is well worth your time to keep in scope as you're doing things. And the reality is in this business, things just tend to fall apart. We end up with defects in our models, defects in our algorithmic selection, defects in requirements, and defects in implementation. So how do we manage all this? So how do we mitigate these defects? Well, there's obviously many methods for defect management. There's lots. You can go through the literature and see them. Again, we're going to focus on defects that get put in during software construction. So we're going to talk about techniques for software verification in an HPC environment. The three that I'm going to talk about are what I call this complete development lifecycle, and then we're going to spend most of our time on unit testing and then design by contract. As I said, this list is by no means exhaustive, nor does it constitute a complete software quality engineering process. That's not what I'm here to talk about today. Notably missing are reviews. People often, anytime you're involved with this, people like to talk, well, what about code reviews and code reviews? We do them, they work. I'm not here to talk about them. You've probably, anytime you've gone to something like this, you've heard all about things like code reviews. We're not gonna worry about that right now. However, the methods I do talk about the three I do talk about can help catch defects before they become a really unbearable or unreasonable expense. All right. One of the most common places that affects us in scientific software development are this issue of requirements. Requirements management is really difficult, and that's because they're very difficult to pin down because our vector often changes as we learn new things. We start with one model, we start running some problems, we realize that that model isn't sufficient or has sufficient gaps, or is not sufficiently addressing physical phenomenon that we need to investigate. And so we're constantly changing our vector. The second part is that as a community, we're usually pretty good at knowing what we want, but we're really not very good at saying it or communicating it well. And since requirements at this level, at a lot of our levels, have to do with, person A coming and talking to person B and actually speaking the same language, there's often, we're often talking at cross purposes, okay? So one of the nice things about software verification, if practiced well, is it can help, disambiguate this, fluffy language-based requirements into functional specifications. Hopefully I'll elucidate that a little bit more clearly as we go. Furthermore, as requirements change, software verification helps ensure that the software is keeping pace. So often we're constantly changing, this vector is going to change. And the important thing is to realize this going in, right? We don't operate in a waterfall model. We can't easily to say we're going to do A, B, C, D, and then we're going to discover new science, right? Often what we often try to do is we look at A, we hypothesize A, we do some testing, and we realize that we have to make a correction to that hypothesis. So it behooves us all to know that the requirements are going to change going in and to develop processes for dealing with that change. So the ability to be agile is very important because change is simply going to be our mode of operation. So agility is really key. So we want to, any processes we want to develop, and ours are not the only ones, certainly, has to be something that can enable rapid prototyping and testing of new methods, algorithms, and features. Okay, let me talk about what I mean is the complete development lifecycle. As I said, this is a phrase that we've actually made up. It has no meaning outside of this, out of the context I'm going to say. Some people may actually refer to it elsewhere, and if I'm you know, burglarizing a common term, I apologize for that. Anyway, what we take this to mean is that our developers are responsible for the complete implementation of code features, and that includes requirements, derivation, construction, deployment. One of the reasons we like to do this is for many ways, for many reasons, and not least of which is we try to avoid pigeonholing people into simply doing one aspect of code. So for example, we try not to have people that, oh, this guy just does communication libraries and this guy just does linear solvers. Obviously, people tend to gravitate naturally to areas where they're strong, and we don't discourage that, but we want to make sure that our code base is developed such that everybody has some level of engagement in different parts, right? Obviously, in really big projects, you have to manage that a little bit more carefully. It's not realistic to expect that somebody who's writing a materials package is necessarily going to be spending a lot of time working in the CFD or flow part, but maybe within that material side, they're working in all aspects of that particular component or aspect of the project. One of the things that's important about this whole process, though, is that documentation and verification is kind of implicit in each phase, and that we don't have people just writing code and someone else coming by and saying, okay, they're commenting or documenting this code. And that may sound ridiculous to you, but I actually was on a project back when I was at Los Alamos where they were actually trying to find people to go in and write comments in other parts of code that because they had several developers that refused to do it. So they wanted actually the people go in and just after the fact comment sections of code that other people had written, which sounds like a pretty terrible job actually. So we don't subscribe to that particular practice. You know, when you write when you write a part of code, you're responsible for its documentation, its testing, and its analysis and everything else. And really this can be summed up in the final statement that developers are responsible for all phases of code development. Okay, we don't want to, basically this is, you know, when you're developing software, you're responsible for it, for the whole thing. Okay, I think we agreed we were going to try to, as I go into these next sections, I would stop briefly and pause if there were any questions. Ashley, should I continue or are there any questions?
Right now, there are no questions in chat. Just a reminder, if you would like to ask questions, please put them here in chat or in the Google Doc, and we will prompt Tom at specific intervals throughout the presentation.
Okay, so now I'm kind of getting into the meat of what I really want to talk about in terms of techniques. I'm going to talk about unit testing. There are lots of teams that do various types of testing. We don't have the only silver bullets here. These are techniques, again, these are techniques that we use. They've worked effectively for us. One thing to remember is something that works really well for Team A isn't necessarily the same process that's going to work perfectly for Team B. So view this as something to just see how somebody else does something. If you find value to it, great. You know, certainly feel free to take it and modify, merge to your own needs. That's the important thing to remember in all of this, is that everything should be done in a way that fits your team. There's a lot of different ways to skin these cats. I hope I'm not offending cat lovers in the audience, but there's a lot of different ways to make this work, and there's no right answer. I think the important thing is to be exposed to lots of different things and find out what works for you and your team. But anyway, we use unit testing as a form of software verification, and the idea is to ensure that each part of a software will perform its contracted task. Okay, the effectiveness of unit testing is really enhanced by two code design practices, acyclic code design and design by contract. I'm going to talk quite a bit about design by contract later, and I'll be explaining what I mean by acyclic code design in a few seconds here. And we actually practice a method of unit testing in which our tests are written either before or concurrently with our executable code. So our standard edit, debug, test workflow is generally where we're implementing a class or a component, and actually the tests are being written side by side. And in some cases, we've actually even had a team of developers actually write a series of tests and then develop the actual component at the point in time when the tests all pass. You in some sense know that the component is ready for some level of deployment. That works really well for when you're testing APIs or working through the kind of iterative design process for APIs when you're trying to hook various components together. It's not, I don't find it quite as effective for low-level code, but it can really help flesh out what an API needs to look like.
Hey, Tom, may I interrupt you here?
Yeah, sure.
So we did have a question back probably on a little bit earlier slide, and the question is, have you evaluated other development cycles in depth?
We've definitely looked at different programming models and development lifecycle models. We use kind of our own version of Agile. You know, we've played with various concepts from extreme programming, but we find for us what works best is kind of an iterative development lifecycle that's built with a kind of Agile. We use like a Kanban style, project management approach. That works best for us, and as I said, ours is kind of a hybrid. It doesn't really 100% fit into any single lifecycle model. But as I said, you can, I think these are the types of things where you want to look across the world of different models up there and pick and choose the right components that work for you. One thing I personally would advise against is trying to adopt the letter of the law of any given process. For example, Scrum has become really popular. Scrum and Kanban are two kind of agile management, project management methodologies for managing a software lifecycle. I wouldn't get hung up on like, okay, we have to, on overly defining roles. I find that to be too restrictive myself, but for some teams it can work well. Let's see. So let me move on here. I hope that kind of addressed that to some degree. So what do I mean by acyclic code design? So one of the things I've tried to do in this particular presentation is to enable, is to actually use real examples from our code base. So that may make these, the idea here, hopefully for some of you is, not to evaluate the quality or lack thereof of our design, but simply to show that these techniques we're actually using them in our real code, and we're actually applying them to real examples. I'm going to use one contrived example later on just because it's a little bit easier, but I'm going to try to do everything in real examples here because I think that brings the point across a little bit better, but it does make things a little busier to some extent. I don't expect you to follow the details of what I'm showing here except for one simple thing, and that is what I mean by acyclic code design is simply meaning that there are no physical or logical dependencies between various components in a code. All associations go one way, and that's all this diagram is meaning to show. Basically, for example, here, there's no two-way association between this domain transporter and physics. Domain transporter in this case only depends on physics. Physics does not also depend on the domain transporter. Besides making your life a lot easier when you're trying to design an actual build system and anything else, this really allows hierarchical testing, which is a real key component of unit testing. When you have a lot of code where you have a lot of two-way dependencies, it becomes very hard to isolate individual pieces and test it, as you'll see here in a few minutes, I hope. So now in the spirit of doing some real-world examples, let me just take a moment and say, bring up an example. And that's not a big Cybertronic eyeball staring at you. This is actually a lot of the applications we do involve looking at computational reactor engineering and reactor analysis. So what we're looking here is at a top-down view of a nuclear reactor core. And one of the principal physics models we do is determining the distribution of neutrons in a reactor core. So I'm going to show one of the small ways we do it so I can make an illustrative example of how we do our unit testing. So one of the methods that we use to calculate the neutron distribution in a core is the Monte Carlo transport method, in which we statistically calculate the neutron field by doing random walks through a core. So what I've shown here is we zoom down into this reactor core, and then we sample a starting neutron indicated by the star. These red regions here is nuclear fuel, gray is the clad, and blue is the water, in case you're interested. And then what we do here is we simply say we're going to sample a distance to our next collision point. We calculate a distance to the next boundary. We move our particle to either the boundary or the collision, depending upon whatever comes first. We tally some state data, and then we do a complete random walk, and then we kind of repeat this many times and statistically accumulate the distribution of neutrons through the core. That's kind of it in a nutshell. Well, what does this imply for the software? What it means is that we have to have some combinatorial or otherwise some geometric model representation in which to do these random walks. So here's an example of one of our geometry packages built using Acyclic design, where we start where we actually, this is built hierarchically, where we say, okay, we've got some simple cell, we can put these guys together into arrays, and then an array constitutes a full geometry. And then we can, the APIs for these things ask the common questions you can expect based on the example I just showed you. So once I'm in a cell, I may ask, what's the distance to the next boundary? I'll need to update the state of a given ray or particle. I'll need to be able to cross surfaces. I'll need to be able to ask for the material ID, et cetera, et cetera. Okay, so given that that's what my model looks like, I can start at the lowest level of this class, right? And we can write a test that unambiguously tests all the functionality of this particular class. So I would call that, for example, if this class is, not if, this class is named RTK. For those who want to know what RTK stands for, it stands for Reactor Toolkit. And I can make an actual test that lives in a test directory right next to the source file called test.rtk cell. All right, there are lots of frameworks that support this type of testing. We use Google Test. For those of you who are familiar with Trilinos, they have something similar called Tupos Test. I'm sure there's myriad other ones that have various levels of features. There's lots out there. You can also roll your own. The details aren't super important, but you know, I would certainly recommend looking at least at some of the other testing frameworks before you go out and spend a lot of time rolling and maintaining your own. Okay, so in the pre-heterogeneous architectural environment, how did we do this? In other words, when I say that, I mean simple MPI communication paradigm. Well, this is actually a part of what that test looks like. Again, this is using the kind of Google test framework. I make a simple test where I say, okay, I'm going to make one of these objects. I'm going to make a simple little pin cell. I'm going to initialize a vector in there, and then I just start testing the conditions. And really what I'm doing here is I'm testing garbage in and garbage out. All of these are kind of done through hand calculations that we actually store in our repository as well. We use it using Jupyter Notebook or various Python scripts, and that way as code changes and you want to figure out, you know, change the conditions of the test, you can rerun those scripts to create new hand calculations, as it were, to update tests. But simply then, I then start continuing, and I just walk through and test the basic API of this class. So I make a vector, I give it a direction, and then I initialize it, and then I actually calculate its distance to boundary. And I say, okay, I've done my hand calculation to say that for a particle, for a point in this point in the geometry in this direction, the distance to the next surface should be, in this case, 0.63. And then I can test a lot of other things. So basically, I'm walking through and I'm line by line kind of testing the API. All right, obviously, when you start getting into heterogeneous computing environments, it gets a little bit more complicated. And the reason is I'm going to give an example using CUDA. So we have this code that has to execute on GPUs as well as on the host side. So in this case, what we do is we make a host side driver. So our kind of our test.cc, the executable that's ultimately going to run, now only has 2 functions. And then what we do is we make a separate header that, again, still just has host side code, all right? And then what we need to do is actually make a CUDA file that looks very similar to what I had before, but now I have to defer the testing to a kernel. So this CUDA code now implements a kernel, and then because it's difficult to run these explicitly run these tests, I pass containers through the kernel. So then I can now run on the right-hand side here. You can see where I'm actually running the exact same test, but I'm filling up the container with the results from this test, so that when they come back to my host side code, I can then walk through those containers and check the various conditions in the exact same way I did before. So I'm running the exact same test. However, there's a little bit of extra work to do when you're running on the device side that you couldn't do when you're just writing on host-supported codes. All right. When I'm doing my side-by-side edit, compile, debug work cycle or workflow, I can run this as I'm going. So I basically update my executable code. I add components or add pieces to my test, and I can run those side by side. This is the output that Google Test gives you. Other testing frameworks give you equally useful output. It's very easy if you have a CMake-based build system to add these pieces. You can kind of see this on the right. We made a simple little macro that allows us to add tests with kind of one line of code. And just kind of then you can just very quickly add those to your build system. And that's how we work this in our compile, edit, debug development cycle. The nice thing about this is that these tests become a permanent part of your repository that you can use to enable continuous integration. I'll talk a little bit more about that in just a second. All right, so going on, if I were developing this class, I've now kind of tested this lower level component. Now when I move up to develop my array, which contains a bunch of these cells, I can realize, or I can basically use that cell as if it's correct, all right? And I can basically then develop up the chain, and then I don't have to worry about the lowest level not being correct. So errors ostensibly that occur as I'm developing arrays have already been worked out after the development of cell. All right, and then as I mentioned earlier, after the completion of a feature, these unit tests remain in the code both for regression and continuous integration testing. I mentioned earlier that we use Python. Yeah, Ashley.
Hey, Tom, sorry, I think this might be a good time to kind of reiterate. I think you kind of addressed it a little bit, but we do have one more question, which is unit testing is generally for building atomic bits and libraries. What do you do when you assemble libraries into larger application packages? In other words, do you develop tests at the system level or the application level?
Yeah, so I think I have a few slides on that at the end. Actually, I don't in this particular talk. So we actually have 3 levels of testing. So we have acceptance testing, regression, verification testing, and then unit testing. What we tend to do is build surrogates, and then we build what look like unit tests that actually execute surrogates to test the components at, and that's simply done at that level to test the handshaking of data, not so much to test the actual execution. We rely on verification tests and our acceptance tests at that particular level, and at that level of testing, we run our acceptance and verification tests generally once per week, whereas opposed to our unit tests are run on a 24-hour cycle. We run 6 different configurations over a 24-hour period, and then we also run all the unit tests on merge requests as well. So our merge requests are, you are correct, whoever the questioner is, that this is done at the component library level, which is where the majority of our development actually is done. At the component level, we rely on surrogates to test the APIs and data handshaking, and then which look like unit tests again, and then we actually run acceptance and verification tests. Those are run on a once per week cycle, and they generally take quite a bit longer. Our unit tests are designed to run on the order of less than a minute. Sometimes they run on the order of a few minutes, but the majority of them run on a very short turnaround time because we have a lot of them. Our current repository has about 550 unit tests. We have another full library of acceptance and verification tests that actually that actually do true numeric verification on our output, and then also test regression and acceptance of coupled components. I hope that kind of answered your question. As I said, that's kind of a next level of testing that I'm not going to get into in tons of detail here. So unless there's more follow-on, I'll go ahead on.
Thanks, Tom.
Okay, so I mentioned earlier about that we use Python and Jupyter Notebook for storing the results of these tests. We find that they're very useful for generating by-hand results. They're also very easily stored with the code, so the test can be modified and examined. I'll explain some of the reasons for that a little bit later on, but in a nutshell, one of the really useful things about unit tests is it allows new developers to come onto your project to see how individual pieces of your code actually work without having to figure out how they work in a much larger application, which is generally much more difficult. And if you kind of have a unit test and then you kind of show like the hand results of what something is doing, it allows the combination of those two things allow new developers to kind of quickly integrate into your project. So this is actually, I've moved on, but this is another part of our code that's actually running a single value decomposition to do a least square separation of a four-dimensional data. And you can see we put our common utility here in our test directory is to call, to make these little NB directories, short for notebook, where we actually store Jupyter Notebook. So for example, we actually, in this particular notebook, we actually build the unit test actually is testing this exact same matrix where we use SciPy to actually do the SVD, and then we can test the values in our unit test. So we kind of keep these things side by side, and they become part of the permanent record of the code and are under version control as well. Okay, that kind of concludes what I wanted to talk about in unit testing. Obviously, we can go on and do more detailed examples. Time precludes me from jumping into too much more detail. So I wanted to move on to the design by contract. Ashley, are there any other questions, or should I just go ahead and continue?
So I have one more question. How do you deal with teeny tiny numerical diffs after code changes? In other words, order of ops changes, sure, and or across compilers and configurations. And do you?
Okay. Yeah. So I'll talk about the performance part a little bit later on. That's a really good, interesting point. One of the things that we tend to do is we tend to truncate numerical values to, and this relies somewhat on judgment, but we generally do most of our numerical values to a floating point tolerance. For things where order of operations matter, for example, in a parallel component where the order of operations can change, we generally just choose a floating point tolerance. For things where they should be rigorously non-changing, in other words, they should be bit for bit, we actually use, Google Test supports a near modulus, which basically can look at basically do differences based on bit comparisons of the mantissa inordinate or abscissa mantissa of a floating point number. That just depends based on the type of floating point values we look at, but generally we use floating point tolerances for data that can potentially change order of change based on order of operations. When it comes to different compilers and different platforms, notwithstanding the fact that those sometimes can change based on the optimization levels of a compiler, generally, when you see significant changes there, it's because you're probably doing something that's not necessarily portable. Now, sometimes that's unavoidable, but what we found is that we can usually isolate lines of code that have non-portable components in it by developing these unit tests, and if we run them and find different results on different machines and different compilers, that usually is an indication that you have some, usually, not always, non-portable code inside your repository. And then you can usually isolate those lines pretty easily. And then you can make the right engineering decisions or right science decisions about whether those are something that need to stay there or something that need to change. We actually rarely see floating point changes that are significant across compilers. We do certainly see them based on order of operations, though. All right, I'm going to move on to design by contract. Some of you may be familiar with this. That is a trademark term. It comes from Bertrand Meyer's book, who trademarked it. There's a lot of details. For those of you who don't know who Bertrand Meyer is, he was the kind of architect behind the Eiffel programming language. If you ask what Eiffel is, it's largely a, God, I hope he's not on the call here. It's a largely academic programming, object-oriented programming language. I don't know of any applications that are in use on any of our HPC machines that use Eiffel. I don't know of any compilers either that are on those systems, but I'm sure there are some somewhere. But it does have a lot of interesting details about design by contract, and if you ever want to look at it, the references on the slide. But basically, DBC, as I'll refer to the design by contract from now on, really what it does is it enforces function contract by testing input, execution, and output of a function. And then again, it's a software mechanism for kind of disambiguating the requirements on a function. This is what I went before when I say, you know, write me X, and you take X to mean one thing, and I have an intent that's another. Design by contract can help actually disambiguate our fluffy human language, and I'm going to show that in the next example. For those of you who don't like using trademarks, this is also known kind of in the open source world as programming by contract and contract first development. So if you see those terms, they refer to the same thing. All right, some languages, Eiffel being primary in this, have built-in support for DBC. For us, we actually implement this in our codes using, for our small number of Fortran kernels that we still support, we use M4, and we use a C preprocessor for the majority of our code, that's C and C++. The nice thing about this is these things are toggled at compile time. So you can add this test in there, and some of our tests are very expensive, and they can be removed in your optimized production code. So they impose no cost in your actual code performance at the end of the day. One key part of design by contract is rigorous type checking, and the nice thing is that our modern languages, C++, and obviously all the modern flavors of Fortran, assuming you don't use Fortran 77 extensions in your new Fortran, in other words, wildcard arrays, are automatically checked by the compiler. So the things that we do want to check are input conditions, execution conditions, and output conditions. So let's look at an example for how this all works. All right, so this is my contrived example. I tried to, I'll show an actual example in our real code where we use this, but I think it's really easy to illustrate this if we use what's a little bit of a contrived example. So you're asked to provide a routine to calculate square roots. As I said, this is manufactured example. I'm sure none of you will ever be asked to do such a thing. And being a fairly clever fellow, you realize you can solve this as a nonlinear problem using Newton's method, and you deliver your unit tested verified solution, and there it is. Obviously, this has a lot of problems, and that was done by design here because I want to illustrate the concept. So anyway, I write my very simple function. I test it on several numbers. I get the square root. Everybody's happy. I move on. Okay, but there's trouble. Okay, what's some of the trouble that this causes? So some indeterminate time later, and this is very common, we deliver some piece of code and somebody else starts using it 3 months, and if you're like me, constantly multitasking, moving from thing to thing, and somebody comes and asks you about something you wrote 3 months ago, you can't even remember what you did 4 or 5 minutes ago, and now you're in trouble because you haven't figured out, you have to kind of context switch and all the problems that involves with. But some indeterminate time later, and you've moved on to more exciting things, you start getting complaints or bug reports. So for example, and if you run that little code I had, you'll find that this is true. So John on your team has spent 2 weeks tracking spurious results down to your square root algorithm that returned a value of 200.5, which has a tolerance greater than 1 e to the minus 6 for a number that he was taking the square root of, which is 40,200.25. Tara also has a problem with you because she's doing spherical harmonics in complex space and tried to take the square root of -4 and got -4.801, blah, blah, blah. So you reply being kind of like more interested in what you're doing now, that your routine was thoroughly tested and performing in design, so, you know, go to hell, why are you bothering me? And we have pandemonium on the software team, right? This is very common. Certainly it's been common in a lot of projects I've been associated with. Maybe it's not in yours, but my guess is it has been at various times. And so what is this? This is really a defect resulting from ambiguous requirements, and nothing is more common, right? So one of the ambiguous requirements is you were asked to calculate a square root. You didn't assume that, you just assumed the tolerance that was acceptable. So I assumed that this was going to converge to some reasonable tolerance, right? Or I didn't even care about what the tolerance was. I didn't test it to a tolerance that mattered, all right? Also, I maybe didn't assume that somebody would be actually using it for complex numbers or complex math, right? So I didn't worry about something, how to handle being given a negative value. So how could DBC have helped? All right, so let's look at this, and now I've added some DBC statements to the exact same routine. So the first thing I did is decided that when I was writing this, in lack of the fact that somebody told me to write a square root function and didn't give me any other guidance, that I was going to assume I wasn't going to deal with complex math. So the first thing I put in is a requirement that the value entering is going to be greater than 0. All right, I've made that decision. Maybe it was the wrong decision, but at least it's in lieu of the fact that I wasn't given any other requirements of the decision I made. And second, I'm going to check for a tolerance, and I've decided that I want my tolerance. I'm only going to solve this to some tolerance of 1 e to the minus 6. All right, so now I'm ensuring at the end of this calculation that it's only going to be greater than 1 e to the minus 6. All right, what's the moral of this story? Well, this clearly won't win any Program of the Year awards, but the point is that I've actually added contracts to show both developers and clients how I've codified these potentially ambiguous directives. In particular, if you are doing reviews, one of the nice things about DBC, and I'm going to go back here, is that these are, if I'm the reviewer of this, I immediately see, based on the require and ensure statements, exactly what expectations the developer wasn't intending when they wrote a particular function or a particular piece of software. So if I were a reviewer, and maybe since I was going to be one of the ones using this down the road, hopefully I would have been chosen to review this, I would immediately see that the implementer decided that this was not going to handle complex math because it's right front and center, right? And then I could then say, hey, wait a minute, this needs to be able to handle complex math. So very early in the process of developing this particular piece of code, I'm able to detect the problem before it gets into production and before people start using it 3, 4, 5, whatever months down the road. All right, so that's the way we can handle certain things at review time to determine if the requested service is doing what is required. And then downstream, even if that function is used in a manner that is outside of our design parameters, at least we know. These required insurers throw C++ exceptions. So if someone were to use this where they needed a tolerance of 1 e to the minus 14 or whatever IEEE tolerance or tolerance was required for a given application, at least when they were calling this, they would get a message that says, hey, this didn't calculate the value to the tolerance that you were expecting, okay, or were requiring. And so that's something that, again, is useful because it isolates or pinpoints where errors or potential errors are at least coming from. All right, what's a real example look like? So let's go back to our distance to boundary, our example from earlier where we're tracking through geometry. So this is the distance to boundary, the device implementation of our distance to boundary function. Again, it takes a spatial vector, a directional vector, and then a state. And the first thing we do is check to make sure, for example, that the directional vector is a unit vector. So one of the requirements, for example, of this distance to boundary is that it does not take an unnormalized direction vector. It only takes unit vectors. So the first thing it does is check to make sure that the magnitude of that vector is within 1 to within some tolerance. The next thing it does is to make sure that the position of the point is inside the object where it's calculating its distance to boundary. All right. Then it does some work to calculate the next distance to boundary. And we check, for example, in the various parts inside of here that the distance to boundary that we're actually calculating is greater than or equal to 0, because we shouldn't be getting a minus distance to boundary. And then when we leave, we also check to make sure that our distance to next region, once again, that final region is greater than or equal to 0, and various other conditions that should be true when we exit if this function actually executed as designed. Okay, I'm moving on kind of to my summary pieces right now. Ashley, I'll stop again real quickly if there's some questions.
I do have a few questions. So back on the previous slide, the distance to boundary condition example is powerful, but do you use documentation statements as readable contract information for functions?
So I guess what you're saying is are these actual contracts, do we have a mechanism for actually exposing, pulling these out and making it part of the documentation for the function? Is that, am I reading that function correctly? Or am I restating that question correctly?
So
I want to make sure I understand the question.
No, Joseph says no. So let me see if I can get more clarification on, or maybe Joseph, if you're able to unmute yourself. I can unmute you. Yep.
No, do you add a layer of documentation that tells the developer that these sorts of contracts are included in the code below as sort of a human readable summary of what's going on?
So we actually don't do anything special with that currently. We simply, if you wanted the truth, what we do is we have editing, we have basically supported editing modes for both Emacs and VI that highlight those as keywords so that they stand out in different colors. But other than that, we don't actually extract them in any formal way to make them as more, directed contract specifications right now. One certainly could do that, though.
And then, Tom, I have one more question. Sometimes having to recompile to get the distant boundary condition checks enabled causes behavior to change. Do you have much experience leaving the DBC checks in at runtime and just enabling, disabling as needed to debug a given issue? How about a cost threshold for controlling enablement, disablement of DBC checks? So we don't do it based on the actual cost of a given check. We have different, what we do is we have our toggling, we can actually turn them off by type. So we can, for example, turn off all checks and ensures but leave requires on. We can turn off requires and leave check and ensure on, and we can leave ensure on and turn off check and requires, and then we can put any combinations of two, so we can leave require check on, check ensure, require ensure. We don't have them based on level of complexity of the test. That would certainly be another option that could be added. So for example, you could have a require level 1, require level 2, require level 3. So for example, it's a good point. So we actually have, for example, in some of our solvers, we have certain diffusion solvers, for example, that use precondition conjugate gradient as a solver. One of the things, one of our design by contract checks we actually have in there is to check that the matrix is SPD, which of course is just as complex a check as doing the solve itself. That's a test that obviously, even if you were trying to debug a larger issue, you don't want on.
and we actually generally just, generally turn that one off and leave it off, and we just leave it in its documentation. So that's actually a good point. That's something we've talked about doing, is actually having the ability to test, have certain high cost tests on as part of, so that you could actually control based on cost. We don't currently do that, but it's actually something we've talked about.
Thank you, Tom.
Okay. So let me summarize what kind of I've gone over here, and that is the purpose of unit testing as we use it is to provide software verification as close to construction time as possible. Again, that's the key takeaway. Any concepts or methods you can use as part of your software development process that can help isolate and detect defects as close as possible to their introduction is just going to basically save you lots down the road. Again, the idea is that we know going in that none of us unfailingly write bug-free code. We accept that, and so we come up with a process that enables us to find those defects at construction time. It helps provide an automated explicit review of the code, and it enables continuous integration. So one of the key parts of continuous integration is the ability that on a given merge request, it runs the entire upstream and downstream tests, of which unit tests are a part. Assuming all those unit tests pass, that basically constitutes a complete release or a valid release of the software. That's the fundamental basis of continuous integration. All right. One mechanism for reviewing is to actually have one developer write tests and a primary developer writes the code. We don't really do that. It kind of violates our complete software development cycle, but I throw it up there. It does work for some teams. We do this where we write the test before we write the code, but we generally have the same team writing both in that particular case. But it is a mechanism for, since actual visual reviews can be very difficult for some teams to implement, this is a way to kind of build it into the engineering basis as opposed to having it be just a process basis. One of the things, there was some talk about porting. One of the things that we found to be immensely useful is that unit testing really does make porting to new platforms a lot easier. One of the first things you do when one of the first things can happen, especially in legacy code, you move to a new platform, you run a problem, and you get lots of different answers that vary in floating point to floating point precision. And the question is, are these real differences due to some legitimate compiler issue, or are they simply floating point changes? And if you have a sequence of unit tests that actually run every single part of your code, you can often isolate where those things are occurring. It's much easier to find esoteric compile and link time errors, especially for those of you who are doing device-based programming, whether on FEEs or GPUs. You know that the compilers, when something goes wrong, spit out a really, really long list of stuff. It's much easier to pin that down when you're writing a single unit test that's testing one or two small pieces of code than trying to do it in in a million-line application and trying to compile all the code at once. DBC is really useful to verify interfaces to client code. So when you're trying to hook two different pieces of code together, two different components, say, for example, a CFD code to a material analysis code, having DBC along the APIs is really useful for validating and verifying the handshaking between those two components. As I mentioned, DBC incurs no cost in your production code. That all gets compiled out when you're outside of your debug cycle. It's much easier to run profiling memory and development tools on unit tests than it is on a full executable. Anybody who's tried to analyze a million-line application knows this, that often our profiling tools often choke on just the sheer size of the application. Another thing that unit tests, in particular DBC, provides is that these become unambiguous statements of code design requirements. It gets away from this fluffy language that we have a lot of problems with. A really useful use case for us, we're constantly going in and improving various parts of the code. I use improvement in scare quotes there sometimes, but one of the things that is often common is to go in and say you found a part of your code where you were using, for example, an n-squared algorithm and you want to replace it with an n log n, right? Ideally, the unit test should not change other than it should get faster, right? The underlying implementation shouldn't change the output of a given API that is tested in a unit test. So one of the things you can do is go in and change the inner workings of various parts of code. And if you have a well-designed, relatively complete set of unit tests, that gives you a certain amount of confidence that you haven't fundamentally changed the actual operation of the code, you've just changed its implementation. I think this is related to a question I had earlier. One of the things that we also do is we incorporate timing data, and we actually get a time history profile of our code performance, because we basically get reports on this weekly. So we run our automated unit test, and it helps us kind of, these timing histories can help us catch inefficient or costly implementations by just looking at the time profile of the code. Another thing that we found to be very useful, especially when you're bringing new people onto a code project, is that your unit tests really do provide a simplified usage documentation for a piece of code. For example, in what I showed earlier, a new developer could easily learn the mechanics of, for example, that geometry package by simply studying the unit test and instead of trying to read the code and then trying to discern its operation in the context of a much larger application. It's only fair that I mentioned disadvantages and cost. There is an upfront cost with doing unit testing and design by contract for that as well. Generally, in our experience, it's about a cost of 4 to 8 to 1 in writing code with unit tests. I would argue that that cost is minimal compared to the cost of debugging throughout a product lifecycle that inevitably results when errors get introduced and you have no idea where the error was introduced. And now you've got a big application that's running a big model, so you've wasted a couple million hours on Titan or something else, and the results aren't correct or the code crashed, and now you've got to go out and figure out, based on your last set of commits, who introduced what error and where in some large application. I view that as a much larger cost. Some teams may not. It just depends on your work cycle. In general, I think that the disadvantages are few unless you have developers who unfailingly write bug-free code, which I'm sure we all have many of. But the reality is they don't really exist.
Hey, Tom.
All right. Obviously, yeah, go ahead.
I know you're wrapping up. I just wanted to say we've got some questions coming in, so I think I'll hold those until you're done, but hopefully people can hang on 2 or 3 minutes so we can address these questions.
Sure, yeah, just one more slide. Last two things, codes that are not structured according to acyclic design concepts. It's very difficult to write unit tests for those, just simply because it's very hard to separate individual pieces and write tests that can really test one thing. It's not so bad if you just have 2 small pieces that have two-way dependencies, but in a big application, if everything has dependencies to everything else, it's very hard to separate and actually write meaningful unit tests. And then unit tests are most effective when, like most things in life, they abide the 80-20 rule. If you literally try to write a unit test that tests every logic path through a given code component, obviously you'd spend all your time writing tests and none of your time writing codes. And the key is to kind of finding that sweet spot where you're testing, the functional path and the primary use cases of a given application that gives you the reasonable coverage, but without going that extra length that adds a ton of time to writing the test. And that's simply done through experience. Finally, I just want to say that, yes, we actually do this. This is about a month-old snapshot of our code base. As you can see, the actual test code, for example, in our C++ executable base is about the same number of lines of code as the actual executable code. The total lines of code in this base is about 700,000 lines. So, and DBC, we do DBC between a 10 and 20% level. So 10 to 20% of our code is DBC statements. And these numbers are similar on the CUDA side as well. On Python, we tend, because we use Python for a lot of post-processing as well as pre-processing, we tend not to have quite as much design by contract on the Python side. But in the executable code, we have a ton of test code. Some final thoughts. Again, my one takeaway, cost of defect resolution increases with time from defect introduction. If you use that as your guiding principle, there's lots of different things you can come up with to address this fact. So you certainly don't need to do what we or others do. Find something that works for you. And then applying any of these principles sometimes adds some upfront costs, but it does have the advantage of catching defects and should reduce downstream costs significantly. Ashley, that's all I have. So I guess, yeah, if we have some questions, we can go through those as well.
All right. Well, thank you very much, Tom. So far, I have just a handful of questions, so I'll try to take these one at a time. How often do you have high-level design reviews of your project, and how do you evaluate new software engineering technologies into your development process? As we know, adding new tools can be difficult in larger projects.
Yeah, adding new tools is definitely a big challenge. I'll take your first point first, though. What we tend to do, our general process for developing new features is that we first start by actually producing a methods document where we start by deriving or at least stating all the equations of a given numerical method that we intend to implement. Then we have a fairly, we actually work in a single room once per week where all 6 people on our team are actually working in the same room, and we actually then discuss high-level interface and designs there. But basically, we do design by sketching. We don't have a formal UML process or anything like that. But what we do is we identify sub-teams that are going to do a given feature. We build issues for that, and then we basically the design review is done through that kind of informal process. But all of our code that gets into our code base goes through a formal merge review or merge request process. So, for example, all of our development is done on topic branches. So when topic branches are ready to be merged, they go through a merge request, and all merge requests require 1 or more reviewers. That's enforced. We use GitLab here at the lab. Unfortunately, our code is export controlled, so we can't put it up on GitHub. But through GitLab, and we actually have the setting set that topic branches cannot be merged until they've been approved by at least 1 other developer. So all of our merge requests go through a formal review process that way. We don't tend to do quite as much on the front end in terms of design review. We tend to backfill that at the back end more. As far as looking at new tools and for doing things, we have a team that's pretty interested in kind of looking around. I generally once or twice a month will just take an hour or 2 and peruse what's out there. Certainly that's something that you want to do regularly, but it's probably the hardest single thing to manage, and I don't have any great answers for you about how to do this, but to look at what's out there, because there's constantly new stuff coming online, and it's trying to balance out what you're trying to achieve versus if you just sat there and looked at what new tools are out there, that's all you would do. So I tend to, on our team, we have a bunch of people that tend to just stay up to date with the literature, as it were, on various tools that are available, and occasionally we'll look at something, and then we, as a team, decide do we want to invest any time in looking at this or not. And we tend to do that in those weekly team coding sessions as well. I hope that addressed that particular question.
So 2 more, Tom. I think one of these is pretty fast, but what are, oh, sorry, my chat window went away. Let me get it back. Here we go. What are routines like device require? Are these routines you have written, or are they provided by the compiler?
Okay, so the device require is simply a macro that we've written ourselves. All of our require check ensures are C++ macros that call underlying assertion mechanism that's based on, that derives from standard error. So I could, you know, if somebody's interested, they can shoot me an email. I'll happily send them the implementation for that, but that's something we've written ourselves. So simply the device require is basically done. The reason we call it device require is because to run on a, you know, to run through CUDA to run on device, it can't be the same implementation as the host code. It has to be a device compiled function. And it also doesn't throw, it just throws an assertion. The assertion catching in CUDA is not quite as elegant as what it is on the regular host side. So it'll throw an assertion, but you tend to get a lot of gobbledygook, which is, of course, why doing this in concert with unit tests become even more important.
So, Tom, we only have one more question. I know we're really running over. And this one's kind of maybe a longer conversation, so maybe I'll just throw it out there. And we are collecting these questions in Google Doc, and we'll put answers to them. But basically, and I know we struggle with this where I work too, is do you have kind of like general rules, you know, for testing, and then what advice do you have to try to get people to actually adopt and, you know, basically go by these rules? Do you have any good
yeah, so we actually, yeah, I'll answer it quickly. Certainly I'd be happy to have with whoever's asking, I'd be happy to, if they want to talk about it more, I can tell them what we do. But in a nutshell, here's what we do. We actually have a developer's manual that has a list of language usage guidelines and then testing guidelines for how, for example, how to write it, you know, create a unit test. We have automated tools that will build a testing template for you. And again, we have the macros for very easily inserting them into our build system. So we have all the tools, and we have documentation on how to use those in our programming manual. That's at, if people are interested in going there, if they're at Oak Ridge, they can go to xnilo.pages.ornl.gov. Our development manual is there to give you an idea of how our developer's manual there, about how it goes, how to do that. The second thing we do is through our merge request process, in a nutshell, or in its basic essence, merge request doesn't get approved unless there's a unit test for every class. It doesn't go in. So you can write the greatest code in the world. If there's not a unit test, it's not going to get approved by anybody on our team.
Thank
so that's
you.
how we enforce it.
With that, I will turn it over to Osni.
So thank you, Tom.